For a long time, there has always been confusion about what the correct expression for the energy momentum of light passing through a material medium is. And there have been a lot of proposed tensors, but the most famous ones are called the Abraham and Minkowski tensors. And in our paper, we would be studying something called the Abraham-Minkowski controversy. Um, some features of these tensors are that Minkowski tensor can be derived from your Maxwell's macroscopic equations, and it is a non-symmetric tensor, whereas the Abraham tensor cannot be derived from any first principles, but it is a symmetric tensor. Uh, the most simple case, in the most simple case of a plane wave, your Abraham and Minkowski tensors are given here, and qualitatively we see that there is a difference between the energy when you're when you describe your energy momentum tensor using the Abraham tensor, or when you describe it using the Minkowski tensor. So recently it was understood that neither of these forms is completely correct on its own. So what physically has any meaning is just the total energy tensor, where your total system is the system corresponding to both the electromagnetic wave plus the material medium. And it was concluded that your Abraham and Minkowski tensors are just corresponding to different separations of the same total energy tensor. In our paper, we see how this formulation can be done using classical field theory, and we try and derive both the Abraham Minkowski tensor and show which form of the tensor is best used in which condition and which cases.
In this section, we will consider a general Lagrangian of different fields. And for this particular Lagrangian, we will derive conserved quantities and conservation equations. To do this, we use the Northern second theorem. We impose local gauge symmetries on the Lagrangian, and Northern second theorem guarantees us a conserved current. After we've obtained our stress energy tensors, the angular momentum tensors, we will perform a sort of gauge change which will allow us to choose a suitable representation of the stress energy tensor. And we will see that this offers us many advantages. Once we have this new stress energy tensor, we will explore the new balance equations and see their implications in different systems. So we begin with a Lagrangian density of n fields. The Lagrangian depends on the fields and their derivatives. And we also account for the fact that the fields may have some internal structure, microstructure. That is, they can sort of mix or interact in their own internal space. So we will now impose local symmetries on the system, as mentioned, and we'll obtain conserved currents. The first local symmetry we impose is that the Lagrangian must be invariant under spacetime translations. By definition, the conserved current for this symmetry is a canonical stress energy tensor, which is outlined in equation 1. Similarly, uh, from the invariance of the Lagrangian under Lorentz transformations, we obtain a conservation equation for the spin angular momentum and the orbital angular momentum. The orbital angular momentum comes from invariance under rotations, and the spin comes from invariance under boosts. These are outlined in equations 2 and 3 for spin and orbital. And we further note that the spin angular momentum density depends on this particular expression skl. These are the usual spin generators of the internal space that the fields are in. So the spin part is non-zero only if there is some internal structure to the fields themselves. If the fields are completely independent and there is no microstructure inside, then these SKL terms are simply zero. Uh, Now we define the total angular momentum as simply the sum of the spin and orbital angular momentum densities. This outlined in equation 4. And we can simply add the conservation equations also. The final four conservation equations for the four quantities are outlined here, equations 5, 6, 7, and 8. And these are called as the balance equations. The derivation of these equations uses the derivation of now the second theorem, which can be found in reference number 2, as outlined here. Now, using a procedure called relocalization, one can show that under a particular transformation of the stress energy tensor and the spin tensor, these balance equations do not change. We will not go into the mathematical derivation of this, but what we do see is that under this particular transformation, we can sort of choose a convenient stress energy tensor and spin tensor. This analogous to choosing a gauge that we've already seen in the course. So the particular transformation that we're referring to is this transformation in equation number 9 and 10. X and Y are arbitrary tensors with only the constraints of X and Y being skew symmetric in particular indices. So we can choose any X and Y, and that will give us a new stress energy tensor and a new spin tensor. And correspondingly, the balance equations will not change. Like which is the whole reason we can do this transformation. So now the particular gauge that we choose is so that the new spin tensor outlined in equation 10 is 0. Under this transformation, we will have a unique choice of X and Y. And for that unique choice of X and Y, we'll also get a unique stress energy tensor outlined in equation 9. And this particular stress energy tensor is called as a BR tensor. That is outlined in equation 11. So given a Lagrangian, we can find the canonical spin density and the stress energy tensor. And in terms of that, we can find this BR tensor. And because we define the BR tensor using equation number 9, equation number 12 immediately follows, which sort of tells us the difference between sigma ij and sigma ji. And by construction, because the spin part have been put to 0, the total angular momentum is defined only by the orbital angular momentum, as in equation 13. We note that this small l does not refer to the generators of orbital angular momentum that we saw earlier, which is a second track tensor. So under this new stress energy tensor and spin density, the balance equations simplify quite a bit. But before we write them down, we perform one further simplification. We consider the fields to be either internal or external to the system. For a closed system, all the fields are internal, and for an open system, some of the fields may be external. The crux of the matter is that if a field is internal to the system, and then it must satisfy the Euler-Lagrange equation, because here fields are treated like coordinates, and we all know that under the least function principle, we always pick the path along which the Euler-Lagrange equation is satisfied. Thus, for the internal fields, equation 14 must be satisfied, which is simply the Euler-Lagrange equation. And since the RHS of our balance equations in equations number 5 to 8 have this Euler-Lagrange equation term, the new balance equations will have non-zero terms in the RHS only for the external fields. So first taking the new relocalization to the BR tensor and then imposing this internal and external partition of fields, the final balance equations we obtain are 15, 16, and 17. Now we will analyze these new balance equations in closed and open systems. For closed systems, the RHS of all these equations simply goes to 0, and we immediately see one big advantage of the BR tensor from equation number 70. We have that the BR tensor must be symmetric because sigma KL is equal to sigma LK. So this was not true for the canonical stress energy tensor even in a closed system. The canonical stress energy tensor is symmetric only if the fields do not have microstructure. However, the BR tensor is symmetric in a closed system even if the fields have microstructure. For an open system, the RHS of these equations may not be 0, and in general, we cannot really conserve anything. In closed systems, we saw that all these quantities on the left-hand side, the stress energy tensor and the angular momentum tensor, are conserved because the RHS is 0. For open system, that's not true in general. However, under specific conditions, we can still obtain some conservation equations. We first decompose the BR stress energy tensor in the usual way, where we define the ij element as a flux of the ith momenta, along a surface of constant xj. And sorry, under this decomposition, the stress energy tensor can be written in the form of equation 90, where U is the energy density and PAB represents the 3 into 3 block matrix inside the stress energy tensor. SA refers to the zeroth row with the spatial components, and pi A refers to the zeroth column with the spatial components. So under this decomposition, we now consider different cases. First, we consider the case in which the external fields are time independent. If they're time independent, then we take the I equal to 0 component of equation number 15. Because of this term, del I phi A, if I take I equal to 0, the entire RHS vanishes. Because by definition, del T phi A is 0. Hence, the for I equal to 0, the RHS of this equation is 0. And we obtain an energy continuity equation defined by equation number 20. We can do the same thing for invariance along a spatial translation. That is, the fields do not depend on a particular coordinate. And let's say this is the XA coordinate. Then we have a continuity equation by choosing the A component of the Hartree conservation equation, equation number 50. And the corresponding equation is outlined here. Similarly, we impose two more symmetries. We consider two more cases. One is in which the fields do not depend on rotation in a particular, let's say, AB plane, and we obtain equation number 22. This is obtained from the equation number 16, which is the conservation equation for the angular momentum. We take the AB component of this equation. Similarly, the last case we will consider is if the fields are invariant under boosts in a particular direction, say XA. In that case, we need to take the 0A component of the angular momentum balance equation, equation number 16. And under this, the equation is simply equation number 23. However, unlike the previous three equations, this does not have any physical significance. We will further see that in a medium, the symmetry under boosts is broken, so this equation will never hold anyway. With this, we've set up a Lagrangian formalism that we'll use further in the paper.
Now we come to section 3 of the paper, where we discuss the electromagnetic field and how we model it in matter. First of all, we discuss the macroscopic Maxwell equations, which are merely the Maxwell equations reformulated in terms of the H and D fields. And the usefulness of this is that the bound charges and polarization and magnetization and such of the medium, the so-called microscopic variation in the charge densities and current densities, are packaged into these D and H fields, and only the free charges and free current densities appear in the Maxwell equations. This is quite useful because generally the microscopic variation is a very complicated function, but can be written very simply in terms of this D and H fields. In general, these fields are defined using certain constitutive relations, which are depend on the material, and these completely characterize the response of the material as well. So for the purpose of this paper, we assume that these constitutive relations are firstly local in space-time and secondly linear in the fields. Locality means that we don't have any integrals or convolutions or derivatives or the fields, E and B fields in these relations, and linear in the fields means we don't have any other complicated functions of E and B, no products of E and B, no polynomial terms, just for example, for the D field, we have an electric field component, all three electric field components, all three magnetic field components, scaled by some epsilon and some beta. Epsilon here is the relative permittivity 3 tensor. Mu inverse is the inverse relative permeability tensor. Alpha and beta are the magnetoelectric coupling coefficients. And in general, all four of these are space-time dependent fields, but that still enforces locality of these relations in space-time. Now it becomes much simpler to work with these relations if we package them into a tensorial form. For that, we first introduce the field strength tensor, which is very standard in electromagnetism. It has both indices raised form and both indices lowered form, and very similarly we define the electromagnetic excitation tensor, essentially replacing E with D and B with H in the field strength tensor will give you this electromagnetic excitation tensor. Both of these are by definition antisymmetric, and when we package the constitutive relations, which are local and linear, into tensorial form, then we obtain tensor contraction of the field strength tensor with what we are calling the constitutive tensor chi. It is a fourth rank tensor, and it is antisymmetric in the first pair of indices and in the last pair of indices. Additionally, when your medium is non-dissipative, this becomes real and gains additional symmetry, that if you exchange the first two indices with the last two indices, the tensor remains the same. There is an additional symmetry here. This is very useful because you cannot actually write electromagnetism, the macroscopic Maxwell equations from a Lagrangian unless you have a non-dissipative medium. We'll discuss two simple cases of the constitutive tensor. When in a vacuum, a constitutive tensor is written purely in terms of the Minkowski metric and the vacuum permeability mu naught as such, and it is straightforward to obtain the vacuum relations D equal to epsilon naught E and H equal to B by mu naught from this. In the case of a linear homogeneous isotropic medium at rest, which we more commonly identify as a medium with a fixed refractive index n, we can also write the constitutive tensor in a very simple form given here. Now it is useful for us to formulate electromagnetism using a field theory Lagrangian. So we have for when you're not considering source terms, the Lagrangian is merely minus 1 by 4 Fij contracted with Hij. To add source terms, free charges, free currents, we need to add this extra Ji Ai term to the Lagrangian. Ai here are the four potentials in electromagnetism, and our field strength tensor we know can be expressed in terms of these four potentials as the partial derivative of Aj with respect to Xi and minus the partial derivative of Ai with respect to Xj. So thus we can essentially then the Lagrangian becomes a function of the four potential fields, and the constitutive tensor is also made of essentially space-time fields, but these are external fields to this system. They are not dynamical fields as we discussed earlier, and hence we do not need to consider them when we discuss the Euler-Lagrange equations for this Lagrangian. Also, it is worth noting that when you do a gauge transform on the four potentials, adding a four divergence term of some scalar spacetime field, then our field strength tensor, our source free Lagrangian, everything is unchanged, but the sourced Lagrangian is not unchanged. We can obtain the Maxwell's equations from this Lagrangian, two of them. The other two we can obtain simply from the fact that our field strength tensor can be written in terms of the electromagnetic four potential, because using the theorem of mixed partials we can write that this permutation, if you sum over the permutations of Ijk here in this expression, the mixed partial derivatives of the four potential components cancel out, and hence you get an identity which can be reformulated into the divergence of the dual field strength tensor being 0, and this is completely exactly equivalent to our homogeneous Maxwell equations, which are the divergence of B being 0, 3 divergence, and the curl of the electric field being minus del V by del T. The inhomogeneous Maxwell equations can also be obtained here, but for that we need to use the Euler-Lagrange equations of motion in a field theory perspective. So, in field theory, the Euler-Lagrange equations of motion become that the variational derivative of the Lagrangian with respect to the dynamical fields must be zero. Only the dynamical fields, not the external fields. And this variational derivative can be derived to have such a form, partial derivative with respect to the field minus um the divergence of the partial derivatives with respect to the um, space-time derivatives of the field. And this goes on for every dynamical field of the Lagrangian, hence we get that many equations of motion. So because we have four dynamical fields here, the four components of the four potential, we get four equations of motion, which are essentially for every I here in this equation we get one equation of motion, and these become the four inhomogeneous Maxwell equations, which we generally remember as two equations, but one is a scalar equation, one is a vector equation, so there are essentially four equations. And it is quite easy to check the equivalence here looking at the form of the excitation tensor above, which we've given. We can compute the canonical stress energy tensor for the source term free Lagrangian using the definition of the canonical stress energy tensor we discussed back in section 2. And this includes this theta ij, which is the Minkowski energy momentum tensor. This is defined in any medium in any system as this expression, and this is defined to be gauge invariant, whereas our canonical stress energy tensor in this situation is not gauge invariant due to this third term. So while the Minkowski energy momentum tensor has other important aspects as well, there is one significant to this paper, which is that it equals the BR tensor derived from this canonical stress tensor. For that, we can calculate the spin density using the definition discussed in section 2, and then we go from the canonical to the BR tensor, and it turns out it exactly equals the Minkowski tensor, and hence this is also gauge invariant. The BR tensor here is also gauge invariant. That is when we have not included source terms in the Lagrangian. Once we include source terms in the Lagrangian, then the BR tensor is also gauge non-invariant. There are some additional terms in this equation in that case, but as we'll later see, our balance equations, which are sort of the physical relations which matter, still end up gauge invariant.
Okay, I'm going to be explaining section 4.1 and 4.2. In the section, I've assumed the material medium to act as a background. That is, even though it does interact with the system, that is the EM field, it's not impacted by the system, and it does not satisfy the Euler-Lagrange, that is, it's not dynamical fields. So, the aim of the section is to find some Minkowski conserved quantities. So, in order to do that, I have to find the um, derivatives, that is the divergence of stress energy tensor. So in the previous section, we have shown that for EM field, PR tensor expression that is equals to the Minkowski stress energy tensor. So I'm just going to be taking divergence by substituting for the field strength tensors components and considering free charges in the medium, which would introduce these terms. So just taking divergence of stress energy tensor will give me the balance equation for BR tensor, which is equation 59. So while observing this equation, there are three terms. First is the divergence. Second, I can say it's kind of like a Lorentz force density, which is nothing but the transfer of energy from the EM field to the background source, free sources and currents in the background. And its components are nothing but the work done and the Lorentz force on those free charges. Um, Similarly, the another expression FIM is the transfer of energy from field to the bound charges and currents of the material medium, and it's uh, and in order to satisfy in order for all these three terms to satisfy the balance equation, the sum would have to be zero so that the rate of transfer of energy and momentum from EM field to bound charges and free charges will have to be compensated somehow. This expression for the transfer of energy from EM field to bound charges is called like the effective material force density and it's given with system. And if you notice, it depends on the variation of the constitutive relations which depict the material properties such as like epsilon, mu, like that for one case, permeability, polarizability, all those. Now, I'm restricting the focus to a very special case when the material is taken to be homogeneous in space, that is, any variation of constitutive relations is taken to be zero. So FIM would become zero, and the time dependence also to be zero. To so the spatial and time derivatives both equal zero, so FIM vanishes and taking the free charges and currents to be zero. So contribution by this Lorentz force density will also be zero. So you'll just be left with divergence of strategic tensor, which becomes zero in these two assumptions. So I can say that the strategy Minkowski tensor for the energy momentum in that case would be conserved. So it just means that if the background medium is completely isotropic and homogeneous, and there's also any variations in the considerations, and there is no free charges and currents, the medium would not apply any net effective force on the EM field. But if the EM field is propagating from a medium which has some uh, anisotropy, like it encounters some interface between two homogeneous mediums, then it will react by changing its direction of propagation and the velocity, and it's consistent with previous notations. Uh, just to note that there do exist microscopic interactions between EM field and the atomic molecules of the medium, but macroscopically, it will vanish. Okay, now for the case of vacuum can have free charges, but it won't have any bound charges. So essentially, FIM contribution, that is the effective material contribution, would be zero. So stress energy, the variation of stress, divergence of stress energy tensor would just look like this. And theta has this well-known symmetric Minkowski tensor form. Now for going for a more general case of isotopic homogeneous medium, the consideration takes this form where gamma is dependent on the refractive index of the medium. Okay, now for the balance equation which we got in equation 59, I'm considering both spatial and time equation separately. This is for the spatial component. So it will have four terms. First is the Minkowski energy density, second is contribution by energy flux density, then power density transferred from the external currents, and the effective material power density for the bound charges. This can be easily seen by the form of sigma, which we have defined earlier, which has these energy density, energy flux density, momentum density, and momentum flux density. This is just energy density terms, which while taking the derivative with this power density terms. So these expressions are known, and now taking the case when the free charge disappearance are zero and there's no variation in considerations, then these two contributions for Wj and W1 become zero, thus iterating the remaining two terms over volume P enclosed by surface delta V. And the case when the flux because of the energy density through that region is equal to zero. The Minkowski, there occurs a conserved quantity, that is Minkowski energy, and it's given with the integration of energy density in the medium. Now, similar for the spatial variations, where A lies from A is 1, 2, 3. It will also have four contributions: moment density, momentum flux density, Lorentz force density, and the effective material force density. Similar expressions are known. Again, consider the case when there are no free charges and currents and there are no variations in the considerations. Contributions from Fj and Fma become zero, and we'll be just left with the first two expressions, and again integrating over volume V, surface delta V, and constant flux to be zero, we get a conserved quantity called Minkowski momentum, and they both these conserved quantities depend on E and V field as well as the properties of the material medium through which is depicted in the epsilon mu I basically chi. Okay, so I until now I have arrived at two concept quantities as energy and momentum. Similarly, introducing a new Minkowski tensor density expression in terms of the stress energy expression, I want to find one more concept quantity. So I related with the Minkowski tensor density and the vectorial Minkowski angular momentum density. So and its uh, components are related to the vectorial terms and the flux by this relation. Now again I'll get a angular momentum balance equation given by equation 84 where the system is the Lorentz for torque density contribution and this is the effective material force torque contribution. But the important thing to note is that the material contribution it's not just the antisymmetric part of this XJ FL minus XL FK, it also has an antisymmetric contribution from the Minkowski stress energy tensor, and it will play an important role in essentially determining when is the angular momentum for the system material medium is conserved. So, uh, so just citing this angular momentum torque contribution in terms of the constant relations and putting free charges in currency equals to zero, I get equation 90. And if you notice closely, it not only depends on the four tensor consideration, but it also depends on the some some term similar to generator for angular momentum, but in this case, it's a 10 rank tensor. So in order to deal with this, I'll make some simplifications like going to an isotropic medium, considering a Lorentz transformations such as boost and rotations. So if I consider rotations, then isotropic medium, this term would be zero. That is the spatial components would be zero. Now again, as we said for F again, there do exist microscopic interactions, but there is no effective microscopic interaction. Uh, so okay. Now in order to say that there exists a Minkowski like concept angular momentum, I'll just need to make sure that the 3 cross 3, the rotation component is symmetric. The boost usually messes up the symmetry invariance of Minkowski angular momentum. This is because in under action of boost, chi is not conserved. This para this breaks the invariance of the open system under boots, and so there's always a need for some agent to keep the medium moving. But this in the previous case we had taken to be addressed, so it breaks the symmetry and it will not lead to conserved quantity. This is spin operator relation to the antisymmetric part of Minkowski tensor. So again, just for completeness, writing down the Minkowski angular momentum contributions. This is the balance equation. Its terms with this again taking the case when because there will and there's no flux. I'll get a conserved quantity that is Minkowski and the momentum under those three assumptions.
In 4.3, we discussed the Abraham stress energy tensor. Sort of the source of all the controversy was the difference between the Abraham and Minkowski tensors. So the Abraham stress energy tensor in matter for electromagnetic fields is defined in terms of the Minkowski stress energy tensor as this expression where we are using the four velocity field of the medium. This is again note field. So this is in general dependent on the position and time we're evaluating this at. And correspondingly, a Lorentz factor is defined using the uh, three speed of the medium with respect to ground frame, and pik is a projector rank to tensor again. So this projects any four velocity you have onto the local rest frame of the medium, and essentially this expression is symmetrizing the Minkowski tensor, but we've written it in terms of some more physical operations in a sense, in terms of the four velocity field of the medium, right? And so it has the benefit of being symmetric, but it has the cost of requiring the four velocity explicitly in the definition. So when you do not know the four velocity, then you working with this tensor becomes a little inconvenient. As we'll see later, which tensor use is really a matter of usefulness and perspective. There is no correct stress energy tensor. Now we can of course get it in exact form using the general definition of the Minkowski tensor and in terms of the F and H tensors, and then we can also compute the four divergence of both of these tensors and compare them. The difference terms between these are absorbed into what we call the Abraham four force density, which is some complicated expression, but important is that it exists, and this differentiates these two divergences. Recall the Minkowski energy momentum balance equation, which only had two force terms. If we rewrite that to get an Abraham energy momentum balance equation, so to say, we get three force terms. And in simple situations where we have symmetries of the medium such as homogeneity, time independence, isotropy, and no free charges, the Fj force term, the Fm force term, they both go to zero. We've seen that earlier. The Fa, the Abraham force, does not go to zero even in these very very symmetric situations. Uh, for example, consider the simple case when you have linear isotropic medium. You have constant and uniform permeability, permittivity. The Abraham force is still proportional to n square minus 1 by c squared, n being the refractive index. So unless we are in a vacuum, the Abraham force is in general never zero, and so your Abraham stress energy tensor is in general never conserved. So this is something we lose when we symmetrize the Minkowski tensor. Again, which tensor you want to use becomes a matter of convenience.
We know that in our discussion till now we modeled as the EM wave passing through a material in which the material was kind of a background. Here what we do is we look at the theory including the dynamics of the material. Basically we are saying that as your electromagnetic wave passes through the material is also influenced by your EM field and its dynamical properties also change. We generalize our theory to include any non-dissipative fluid with linear and non-dispersive optical properties. An important thing to note here is that fields which satisfy Euler-Lagrange equations are called dynamical fields. For our medium, we call these dynamical matter fields, and we express our constitutive tensor chi in terms of these dynamical matter fields, where nu is the number density, mu is the force velocity, and phi a are our dynamical fields. And for a system without any microstructure, our dynamical fields tend to zero. And from our discussion before this, we know that this implies that the BR tensor is symmetric. We model our fluid using the laws of relative hydrodynamics, and from there we know that we get these four equations. The first equation corresponds to particle number conservation. This second equation implies that entropy is conserved along streamlines of the fluid, and this x, which is called the Lin coordinate, we introduce this to kind of as a coordinate to keep track of uh, the streamlines where our entropy is conserved. So now the total Lagrangian for our total system is given by the Lagrangian for the electromagnetic field plus for the material. And using the Lagrange multipliers and the conservation equations below, we write our matter Lagrangian as given in this equation, where here LA is the anisotropic contribution to the material Lagrangian, and this depends on the microstructure of the material and is given by number density, 4 velocity, dynamical fields, and the derivatives. And rho depends on the number density and entropy, and this is the thermodynamic internal energy density of the material. So using the Lagrangian, now we get the Euler-Lagrange equations from this. So taking derivatives with respect to psi a, number density, and the 4 velocity, we get the following three equations. And we also use the Gibbs law of thermodynamics, where we introduce the temperature T and pressure P of the material. And using this, we can simplify our matter Lagrangian into this form, where we can introduce something called the effective pressure given by this relation. Now we have our equation of motion and the Lagrangian. We are ready to calculate the canonical and BR tensors. So from the previous discussion, we know how to calculate the BR tensor once we have our Lagrangian. So we just substitute it in the previous equation, and this is the form we get. And the anisotropic energy momentum tensor is just defined using the definition of a BR of the canonical energy momentum tensor, and this is the expression we get. After further simplification, where we use conservation laws and we use the Lagrange multipliers, we eliminate the Lagrange multipliers using the Euler-Lagrange equation. This is the form of matter canonical stress energy tensor we get. And now we want to construct our BR tensor from this equation. To construct the BR tensor, we need to know the explicit form of the spin current density as well as its derivatives. And from section 2, we know how to do this. We just substitute it into the equations, and these are the forms we get for spin current density and its derivatives. And after a lot of math and its simplification, this is the final form we get for the BR tensor. An important thing to note here is that this is the BR tensor for just the matter fields, and this depends on the Lagrangian for the electromagnetic fields in this term here, and in it also manifests itself in the effective pressure term. So now we have the BR tensors for the matter, and from section 4 we know the BR tensor for just the field, and it is valid to use the BR tensor from section 4 because the electromagnetic wave in this closed system is kind of an isolated open system on its own when you isolate it from this system. So taking that into account, we have a total BR tensor is equal to the Minkowski tensor plus the BR tensor derived in 5.3. Here the Minkowski tensor is the BR tensor we derived for j equal to 0. From here we get our conservation equations, del j sigma ij equal to 0, and using the angular momentum we have that del j LKL is equal to 0. And we see that the BR tensor is symmetric and depends on all the dynamical fields of the closed system.
Hi. In the previous section, what we finally obtained was this total BR tensor for the electromagnetic field and the dynamical medium both considered together as one closed system. And we found out that this is just the sum of the Minkowski tensor for the electromagnetic fields, which happens to be same as the BR tensor for just the electromagnetic fields we obtained earlier for the open system with the materials in the background. And the other term is the BR tensor for the material fields. Now what we'll do in this section is write the same total BR tensor, but in a different way, so that one of the terms comes up is the Abraham tensor instead of the Minkowski tensor. So to obtain this, what we'll do is we'll apply the angular momentum identity from the balance equations that we obtained. So this is, if we quickly go through this equation, yes. So this is the angular momentum identity. This is true for a general BR tensor, and we see that we get the antisymmetric component in this way. So what we'll do is we'll take this equation, we'll plug in our total, not the total Lagrangian, but just the Lagrangian for the electromagnetic fields, and the expression we get, some of the terms are going to get cancelled from the equations of motion. That is just the Euler-Lagrange equation for the total Lagrangian for this system. And the equation that we finally obtain is as follows. So this is the antisymmetric component of the Minkowski tensor. And now to obtain the Abraham tensor, we simply plug the antisymmetric part into the general expression for the Abraham tensor, or Abrahamization of the Minkowski tensor, so to speak, and we just obtain this particular expression. And we do something very simple. We just simply write this total sum as, we just define this kappa as sigma minus omega, and then we can obviously write sigma as sum of omega and kappa. And so this kappa is the kinetic energy momentum tensor of matter. Okay, and this equation, now the total BR tensor, has been written in this form. Now, except for this effective pressure term, only matter field dependent terms are in this kappa tensor. So and even this case of the effective pressure not being non-zero, it happens when there is electro or magnetostriction, where expansion or contraction of the material happens with no polarization. If and when you ignore that, which is true for most cases, you just have your effective effective pressure to be zero. Okay, and now the both of those decompositions are physically equivalent, because the measurable quantity is just your total BR tensor. But the Abraham decomposition has a bunch of more nice properties compared to the Minkowski decomposition. First, both of those terms, omega and kappa, are symmetric tensors, and more importantly, so the two terms, so one term contains only the electromagnetic field dependent terms, field dependent quantities, and the other term only contains the material field dependent quantities. So you can write the continuity equation just from as these two terms, which are easily being interpreted as this exchange of energy between these two systems, this system or set of fields. Yeah, and this is not possible for the Minkowski decomposition, because the BR tensor of matter in the Minkowski decomposition only always contains this field strength tensor. So you don't have these decoupled fields. Okay, so now it's time to conclude the entire argument of this paper. So this is just a summary of what we did. So we just considered two different systems. One of them was open and the other was closed. The open system, we just consider the material fields as background, or the external fields, while in the closed system we considered both of those fields into a total system that is closed. Now in the open system, we observed that the Minkowski tensor was a more favorable choice for your electromagnetic field tensor. The energy momentum tensor, sorry. And we showed that even though there is asymmetry in this Minkowski tensor, it is necessary to be to correctly describe the interaction of light with the general medium. Uh, However, the Abraham tensor is not that favorable because the Abraham tensor was not conserved when the medium has symmetries. So what we did to resolve this is just have an ad hoc Abraham force, and the interesting thing to note is that even if you introduce this Abraham force, it is not going to help you in distinguishing whether either of the cases true. Is the Minkowski tensor really describing the electromagnetic component of the momentum within the medium? Because the measuring the Abraham force, when you say that, okay, I'm going to measure the Abraham force, you are already so both of these, when taking the Minkowski tensor or the Abraham tensor, both of these satisfy the same balance equations, but the terms within the balance equation get shifted around when you take the Minkowski tensor or the Abraham tensor. So when you say you're going to measure the Abraham force, you've already a priori done this shifting the weightage between the terms, and that is why you are when you do this experiment, you are going to get your Abraham tensor, but it's not going to exclude the Minkowski tensor because you did this shifting around the weights in the terms a priori and not a posteriori by experiment. Now, okay, and in the second case, when we allow the material to move in response to the dynamic interaction and consider the entire thing to be a closed system, it turns out that the Abraham tensor has the more convenient interpretation because even though like the total BR tensor, it doesn't matter how you decompose it because the measurable quantity is the total BR tensor. But the Abraham decomposition is more favorable because of the properties we talked earlier. And and importantly, as I said, the experimentally measurable quantity is the total BR tensor, and any decomposition of the same is arbitrary. But the Abraham decomposition has these nice properties and is more interpretable because you can write those two terms in the form of a continuity equation. Thus, the entire point of this paper is showing that instead of there's not a notion of this like a correct exclusive energy momentum tensor for electromagnetic fields in a vacuum. Okay, when you divide the total like momentum between the material fields and the electromagnetic fields, such a division is somewhat arbitrary, and it cannot be measured in an exclusive fashion that this division is the physically correct one. The only way you can do is just fool yourself into thinking that if I start with, as we did with the Abraham force, because if you're starting with the Abraham force, you already have made up your mind about the terms in the total balance equation, and so you are going to verify that the sum is consistent with the balance equation, but it does not imply that this particular weighing of the terms is correct. However, as we showed that some decompositions are more convenient than others and yield better to interpretability and other conveniences. And such decomposition, like which one is a convenient decomposition, depends upon the choice of the system and how you formulate it.
Submitted and the solution to that tutorial question. This is a fairly straightforward question with only a couple of conceptual points to understand. The rest is just taking derivatives. So the question asks you to start from the Lagrangian density for electromagnetism, which has been provided here as -1/4 Fij contrasted with Hij. That is the field strength tensor and the excitation force tensor, which the definition of which has been provided here in terms of the constitutive tensor. You do not need to know the form of the constitutive tensor for this, merely the symmetries it has, right? And there are no source terms in this Lagrangian, so you need to derive the macroscopic Maxwell equations in the absence of free charges, hence no source terms. And in a non-dissipative medium, in a dissipative medium, this Lagrangian density does not give the macroscopic Maxwell equations. So a non-distributive medium manifests itself mathematically in terms of x ijkl being equal to chi ijkl being equal to chi kl ij. You exchange the first two indices with the last two indices and you get the same tensor, right? A few useful formulae have been provided. Number one, the four potential formulation of electromagnetism. You should be familiar with the four potential, which is C phi, and then the three vector potential A. And in terms of this, you can write the field strength tensor as del I aj minus del j ai. That is straightforward. Then we have the Euler-Lagrange equations in field theory for the internal fields of an open system, the dynamical fields. This equation, in terms of partial derivatives of the Lagrangian density with respect to the field itself and with respect to the space-time derivatives of the field, this equation becomes zero. This is the Euler-Lagrange equation. You would be familiar with the Euler-Lagrange equations from classical mechanics. This is the field theory version where you're taking derivatives with respect to the field and its derivatives rather than with respect to, say, x or q and its derivatives and its time derivative generally, right? So you do not need to understand the derivation of this. You need to understand how to apply this here. We are using the metric given here, Minkowski metric. We're not putting c equal to 1. Our strength and excitation tensors have been given, the field strength tensor with both indices lowered for usefulness, although you do not exactly need this. It is sufficient to provide the answer in terms of the Bianchi identity or the dual field strength form of the homogeneous Maxwell equations and the excitation tensor form of the inhomogeneous Maxwell equations, both tensorial forms. You'll see these exact forms as we discuss the solution. If you wish to, you can derive the exact three vector Maxwell equations from these, but I don't think that is necessary for the complete solution. So now there are two parts to the question. Number one is deriving the homogeneous Maxwell equations, right? For which we do not require the Lagrangian density at all. The fact that we can write the field strength tensor in terms of the four potentials is sufficient for this. So note that we need to take the derivative of the field strength tensor because the Maxwell equations have derivatives of the fields and the field strength tensor is written in terms of the fields. Yes. So you take the derivative and you get this term. You take the most general derivative del I f j k, and this term, now this is just expression. What do you do with this? You need to equate this derivative to something to get an identity, and the identity will become the Maxwell equation, right? So, and here you realize there are mixed partials happening, right? So it is suggested that we use the symmetry of mixed partials to get an identity. We add similar terms to del I f j k, specifically del j f ki and del k f ij, which are essentially we are cyclically permuting the three indices here I j k and adding all those terms. And then due to the symmetry of mixed partials, all these terms cancel out, which you can check, and we get a 0. Hence we have an identity. This identity is called the Bianchi identity, and this is exactly the homogeneous Maxwell equations. You can observe that more explicitly if we rewrite this in terms of the dual field strength tensor, which I will introduce. Also note symmetrization and anti-symmetrization, the notation we use for that, the round and the square brackets over the indices. Yes. So this is the Bianchi identity. You can rewrite this if you wish in terms of the dual field strength tensor, which is defined as half epsilon Lijk f jk, right? Epsilon Lijk is the Levi-Civita tensor. It is a fully antisymmetric fourth rank tensor, and you can look up its standard definition. If you have epsilon 0, 1, 2, 3, that would be 1. If it's 0, 1, 2, if it's 0, 1, 3, 2, then it would be minus 1. If it's 0, 1, 1, 2 or something, then it would be 0. It is pretty standard. So what we did here is we took the Bianchi identity and we contracted that with the, or rather we contracted the derivative we took initially with the Levi-Civita tensor. And because the Bianchi identity is true, hence we know that this will be true for all L. Because the permutations over IJK will simply give us the signs we need. So the dual field strength tensor has the form given here. We have sort of exchanged electric and magnetic fields from the field strength tensor, and the divergence of the dual field strength tensor becomes zero, derived from the Wank identity. And from this expression, it is straightforward to get the homogeneous Maxwell equations. To arrive at the inhomogeneous Maxwell equations, which without free charges are this divergence of t being 0 and curl of h being d by del t. For that, we use the Euler-Lagrange equations for classical field theory, which are introduced above. And the Euler-Lagrange equations in our problem will be the variational derivatives of the Lagrangian density with respect to ai's must be 0. Variational derivatives are simply the expression I noted above in the question. And variational derivatives occur when we're deriving the Euler-Lagrange equations from the minimization of the action. Yeah. Important to note here are two things. Number one, we're taking derivatives with respect to fields and the derivatives of the fields, not with respect to x or t, not with respect to x or t. Yes, because this is field theory. This is a field theory Lagrangian. So that is what the Euler-Lagrange equations in field theory become. Also, second very important thing to note is that we are taking derivatives only with respect to the AIs, right, the four potential fields, not the constitutive tensor fields, because the constitutive tensor fields are not part of our system. They are external fields because the medium is a background to our system of electromagnetic fields. After that, it is simply taking the derivative. You'll note that the first term in the Euler-Lagrange equations goes to 0 because we have no a mu dependence in the Lagrangian density. We have Fij dependence, which becomes a del Iaj dependence essentially. So only the second term need to be evaluated. And chi is independent of our derivatives of a, so we take that out. We can evaluate the derivative of the field strength tensor with respect to let's say del nu a mu, one of the derivatives of one of the four potential fields. And this is quite straightforward to do. We write it in terms of the canonical delta functions, or in this case they're technically the identity tensors, but you can think of them as canonical delta functions for ease, right? We substitute this into our Euler-Lagrange equation. This is what you get. Product rule, hence we get two terms, right? Product rule on this term. So you get your two terms, and then you expand these out to get four terms. Now important is that the constitutive tensor has some symmetries and antisymmetries. Number one, it has antisymmetry in the first two and second two indices. So chi ijkl equals minus of chi jikl, and chi ijkl equals minus of chi ijlk. Yes, that is encoded here. So that allows us to turn these minus signs into plus signs and exchange indices. Also, we are working in also this antisymmetry has not been given in the question, but it is something which should be straightforward from the fact that h and f are both antisymmetric tensors. Hence, for the sort of definition of h to hold, you really need chi to be antisymmetric in first two and in second two, last two indices. The other is for non-dissipative media, we discussed the symmetry of chi, that ijkl becomes klij and it's the same tensor. The proof of this is out of the scope of this presentation or this question, but for that purpose this has been given as a formula you can use. So use this to simplify our equation 147 into 148, because chi nu mu kl fkl, this contraction simply becomes 2 of h mu nu, and then this contraction will also become that once you exchange the pairs of indices. So you get 8 h mu nu here, the derivative with respect to nu, which becomes del j hij equal to 0, which are the Lorentz covariance form of the inhomogeneous Maxwell equations. It is interesting to note here that we have an 8 appearing. Remember, we discarded the 1 by 8 here because the other side is 0. If we did not have the other side being 0, which would happen when we had source terms in the Lagrangian, then that 8 and this 8 would cancel and we would get the inhomogeneous Maxwell equations with source terms exactly. Feel free to actually I recommend you try doing that as an exercise. It's not difficult at all. It's this with one extra step, and that is the tutored question.